Hello, and thanks for using TickBoom. I've had a student send through this very interesting proof question which reads, if A, B and C are all greater than 0, then prove that A to the 5 plus B to the 5 plus C to the 5 is greater than or equal to A cubed BC plus B cubed CA plus C cubed AB. Now this is one of those questions where you really can go down rabbit holes and end up spending heaps of time on things that don't end up proving fruitful. And personally that is what happened to me. I tried a few different factorizations of A to the 5 plus B to the 5 plus C to the 5 and wasn't really getting anywhere. Interestingly, the student who sent this through then cracked it before I did, so they kind of gave me the hint that you need to use the AM-GM inequality, or in other words, the inequality that you can state between the arithmetic mean of something and its geometric mean. And so even though the student in the end didn't need my help on this, I still want to work through the solution because I think it's a nice way of adding another tool to your toolkit on inequality proofs, this AM-GM inequality. So if I just start by writing out what we're being asked to prove. So we want to prove that A to the 5 plus B to the 5 plus C to the 5 is greater than or equal to A cubed BC plus B cubed CA plus C cubed AB. And it's on the basis that A, B and C are all greater than 0. Now, the way we can tackle this, and it kind of first requires thinking to use that AM-GM inequality that I've mentioned, but also something else a little bit creative, which is to rewrite A to the 5 plus B to the 5 plus C to the 5 as each of these 5 times all divided by 5. And that's how we can get into our format of means. So we'll get A to the 5 on 5 times. So plus A to the 5 on 5, plus A to the 5 on 5, plus A to the 5 on 5, plus A to the 5 on 5. So hopefully you see we haven't changed anything. We've just divided it by 5 and added it up 5 times. And we'll do the same with B and C. So B to the 5 on 5, plus B to the 5 on 5, plus B to the 5 on 5, plus B to the 5 on 5, 1, 2, 3, 4, plus B to the 5 on 5, plus C 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 to the 5 on 5, and then one more plus C to the 5 on 5. So we've simply changed nothing, rewritten this, dividing everything by 5. Now what we do is we kind of group. Notice how we've got 3 items here. So we want to group these into 3 different sets. So we'll get, we'll pick 3 A's, 3 A's, a B and a C. So we'll get A to the 5 on 5 plus A to the 5 on 5 plus A to the 5 on 5 plus B to the 5 on 5 plus C to the 5 on 5. So that'll be our first one. Then we'll get 3 B's, a C and an A. So I've used 3 of the A's. I've used 1 of the B's and 1 of the C's. So now I'm going to use 3 B's, B to the 5 plus B to the 5 plus B to the 5, each on 5. So that's 3 B's gone. And then a C, C to the 5 on 5, and then an A plus A to the 5 on 5. And the way I know how to group it is just to mirror what the solution ultimately has. So the last one will be 3 C's, C to the 5 on 5 plus C to the 5 on 5 plus C to the 5 on 5. And that's the last 3 C's done. An A plus A to the 5 on 5, so that's the last A done, plus B to the 5 on 5, and that's the last B done. So we've regrouped everything into these 3 groups, and now we can use our geometric or arithmetic geometric mean inequalities. So what I can now say is that each of these are greater than or equal to a to the 5 times a to the 5 times a to the 5 times b to the 5 times c to the 5, all to the power of 1 on 5, plus b to the 5 times b to the 5 times b to the 5 times c to the 5 times a to the 5, all to the 1 on 5, plus c to the 5 times c to the 5 times c to the 5 times a to the 5 times b to the 5, all to the 1 on 5. And that's because an arithmetic mean, so in general x1 plus x2 plus up to x to n all divided by n, the arithmetic mean is greater than or equal to the geometric mean, which is the nth root of each item multiplied, so x1 times x2 all the way up to xn. So if you take a series of items, add them and divide by the number, that's the arithmetic mean. That's always going to be greater than if you multiply them together and take the nth root. So that's what I've done here. I've just taken each item and instead of dividing it by n, 5, I've multiplied them and taken the nth root, or to the power of 1 on 5. So now what that means is we can continue this, because that means each of these items to the power of 5, then all to the 1 on 5, these 5s cancel. So the 5s all cancel with the 1 on 5. And we can then simply bring common items together. So we'll get a cubed bc plus b cubed ca plus c cubed ab, which is exactly what we were asked to prove. So you can see how what could have been an incredibly tough proof, sending you down all these wild goose chases, actually ends up being quite a neat and elegant, quite a fast proof once you know what to do. Once you know that this is the technique that's going to help you. So again, like with a lot of things, I think practice is what helps you to be able to tackle these in an exam. The key is just seeing enough so that when you are faced with something, you can dig into the toolkit and hope that in that toolkit there is some technique that you've become familiar with that's going to help you. So with the inequalities, there are a whole bunch of results, things like the triangle inequality, and in this case the AMGM inequality. When you're in inequality space, you've got to think, well, what are all the results that might help me here? So hopefully you found that helpful and interesting, and tick boom.